Good afternoon, everyone, and thanks for sticking so far. Lots of people have already gone home. This is the pre-last presentation, as I understand. My name is Tarek. I work for Twitch, part of Amazon. And today I'm not wearing the Twitch hat. I'm wearing the MPEG hat. And I'm here today with Guido to talk more about the next generation of the new MPEG standard for video encoding. So this session is about 45 minutes. Initially, Guido is going to give a 20 minutes technical presentation, and then we're going to have like 20 minutes of a fireside chat, although we don't have a fireside here. And then we'll leave 5 to 10 minutes for the audience as well to ask questions. So with that, probably Guido will present himself, and we get the technical discussion started.
Yep. Thank you, Tarek. Hey.
Picture. Thank you.
Awesome. So yes, thank you for staying till the end. I'm Guido Meardi, CEO and co-founder of Vinova. And as Tarek said, also in my case, I'm wearing the MPEG hat today more than the Vinova hat. And I'm quite excited about the topic because LCEVC is quite exciting. But first of all, how many of you have ever heard about LCEVC or know what LCEVC is? Oh, fantastic. Awesome. Decent mix. And how many are excited about LCEVC? Well, that's good. You know. So my purpose would be to make sure that 100% of people here will be excited after this. First of all, just to start with the prop, in your opinion, we have here just to show how much LCEVC, despite the fact that it's a fresh new standard from MPEG, it's already alive and kicking, and in this case, really live. This is actually a live channel. As you can see, CNN, it's happening right now. And aside from the content, unfortunately, right now, it's fairly static, but anything could happen. Could you guess how much bitrate this channel is that is up right now, what you're watching right now? I'm sorry? 900 kilobits. Any other bet? That's a good bet, but overshot. This is actually 300 kilobit. And it's actually a 720p at 300 kilobit. Now, actually, to be honest, this is a fairly easy moment, but it holds pretty well also in other moments. It's actually already in deployment in a part of the world. There are a few million people that are receiving this. So this is just to show that despite the fact that it's new, it's getting pretty quick traction. And my purpose would be to make sure that oh, sorry, that's my Slack, and voila, to show why that works. So at the beginning of the presentation, I will focus on what LCEVC is, why it works, how is it possible, and some performance results. And later, as we said, we will get to the more important stuff. So a fireside chat between me and Tarek on what this really means and what's next for this standard. So first of all, LCEVC stands for Low Complexity Enhancement Video Coding, and it's part of the MPEG 5 suite. It's in particular MPEG 5 Part 2. There's also Part 1, which is a totally different thing. And low complexity enhancement video coding, why would we do such a thing? There are many people that would agree that today complexity of encoding is becoming a problem. And it's becoming unsustainable, it's becoming very costly, and sometimes, especially for live, aside from being costly, it makes it very difficult to use advanced new codecs. And in particular, this is a blog that David Ronca, director of video of Facebook now, in Facebook, but previously at Netflix, wrote recently, where he also provokes with the thought experiment. What if the next codec, instead of compressing better, was just 50% faster? Probably would be a very successful new codec, even if it doesn't compress better. And what David is talking about is essentially this, that for the past decades, compression codecs advanced quite well in terms of compression efficiency. The blue bars that became progressively smaller, let's not bug too much into 30%, 50%, whatever, but they became progressively lower and lower. But the price to pay for this better efficiency has been consistently more and more processing power And lately, this has literally gone through the roof. So actually, for the latest codecs, we're talking about very, very substantial increases. This, of course, means also new devices, no compatibility, problems in delivering in the new codecs, and also ultimately costs and trade-offs. But at least it's great because this advance is inevitable, and the new codecs are extremely good at compression. At MPEG, there was a long discussion to say, what if we could do something like this? A new approach that is not a new codec. It's not yet another codec, because there are already a lot of codecs between the ones that are available today and the ones that are coming very soon. But what if we created something that whatever the choice of codec, old, current, new, it made it better and faster. So it improved the compression efficiency a bit, but at the same time made it more efficient in complexity. This, of course, would be helpful, first of all, because it would be a completely orthogonal approach to anything else, but also it would allow immediately to reap the benefits of better compression, to deliver better quality to more people compatibly with devices that are already around or new devices that are coming out. And this is the essence of LCEVC. So essentially, there was a process over the past year and a half at MPEG where initially evidence was brought that this was possible and achievable, and ultimately LCEVC was born with these basics. So this is essentially what the enhancement codec does. It is an enhancement, so it's not a full-fledged codec, but it codes enhancement data. It's applicable to any base codec of whatever sort, both MPEG or AOM or Chinese for the lovers of AVS or AVS2. And from a compression point of view, it brings a codec close or slightly better to the performance of a subsequent generation codec. So if you apply it to AVC, you will get a performance similar to that of HEVC. If you apply it to HEVC, you will get a performance similar to that of VVC, and so on and so forth. Most importantly, hence the name and the first two initials, low complexity. So it reduces the overall processing power for the combination of base codec, so leverage codec and enhancement. And it can be, very importantly, implemented in software with sustainable power consumption, both on existing devices like the PC that I was using earlier and browsers, but also most importantly for these guys, where it's not just about being able to decode, but it's about being able to decode with a certain amount of milliamps because you don't want to drain the battery. And nobody would accept better video at 10% battery drain, a faster battery drain. So it's very important to use the same or lower battery power consumption. And that was a very key requirement for LCEVC. The good news is that these objectives were achieved. So the standard specification was born having achieved these results. And now we are in the phase where the standard is being finalized, in the sense it's been finalized from a specification point of view. It's in ballot, so it should be published over beginning of the next year. But the nice thing is that it can already be used and deployed. And some people, as I showed, are already doing it. Why it is important for operators? Well, very simple reasons. Up to 3 times throughput increase in terms of complexity. This means if you're encoding in the cloud or on-premise, you can fit more channels on the same servers, or you can use smaller servers, or you can save battery power consumption if you're using a phone or stuff like that. Up to 50% bandwidth savings. We will see some more numbers. Of course, this depends on the type of content, depends on the resolution, etc. But we are talking about substantial savings in efficiency, so comparable to a next generation whatever the starting point is. And most importantly, as I said, any codec. So this is not something that joins the battle of codecs. It's actually a tool that can be used by any codec. So it's a very neutral Switzerland of codec world, if you want. In a fun way. Why is this really important from a practical point of view? Because those were technical benefits still, but from a business point of view, this means over 4 times more engagement, because better compression means more quality, more, less waiting time, and all the things that you know and love. Up to 8 times more reach, which means more customers, and up to 50% lower costs. So the benefits from a business case point of view can be extremely substantial. Of course, these numbers depend, but again, we're talking about pretty high numbers. How is this possible? So how does it work? Is there any secret? Very often when talking about LCEVC, I hear words like too good to be true, or how is it possible, it cannot be possible. So my objective would be to make sure that you understand how it works, and the fact that it's not magic, it's actually pretty simple also. That's why it's low complexity. Essentially, the codec works by using another codec at a lower resolution, of course, to make sure that the combined entity of leverage codec plus enhancement takes less power and less bandwidth. One requirement is using the leverage codec at a lower resolution so that it can be focused on fewer pixels, so less processing, and it can be more efficient at cranking those pixels. And then the high frequency, so the additional data, is encoded using a special encoder, which is LCEVC, that is aimed specifically at coding enhancement data. I will show in a bit what enhancement data is, but essentially what LCEVC does is it codes the lower resolution, and then the delta between the lower resolution and the top resolution, top quality, gets encoded with this special enhancement codec. At the decoding side, the video stream, which is a mixed stream containing 2 elementary streams, a normal stream of the base codec and an enhancement stream, which can be packaged as a separate PID or as SCI metadata, or even sent as an independent stream. There are several options. But at the decoder, there is a standard decoder, even hardware, that decodes the base codec. And then the enhancement is decoded separately and overlaid and merged with the base in order to obtain the final output. If you want to see it in a more visual way, this is kind of like how it works at the decoding side, where you would get a sort of thumbnail video or a lower resolution video encoded with the traditional codec, whether H.264, HEVC, AV1, whatever. There's a first layer of residual correction before an upsampling pass. There can be also an upsampling pass here. It depends. It's parametric. There's a correction layer that corrects before the most important upsampling pass that brings to full resolution. And then there's an additional sublayer of residuals that adds the details at the end, also leveraging a temporal buffer. Importantly, as you can see, these sublayers of what LCEVC encodes are not pictures, they are residuals. And that's actually quite important because they are something like this. When you talk about details, this is an example of what LCEVC would encode of a 1080p of, in this case, it's pre-evident, a Formula One video. And you can see that there are a lot of details, a lot of dots, a lot of edges, a lot of text detail. This stuff, which would be high frequencies, is very costly for traditional codecs. If you're using a DCT with big blocks, think about HEVC 64 by 64 coding units with DCT. When you have a single dot, it would be tens of coefficients to encode it. LCEVC is actually meant to encode this stuff. So it has very small transforms, very aimed at high frequencies that are extremely efficient at compressing high details. And so by combining the fact that the normal codecs, the DCT-based codecs, can be quite good with lower resolution, and the fact that LCEVC is very, very effective at compressing this stuff, the combination becomes very efficient. The other important thing is that when you see something like this, you also understand why super resolution or just upscaling can be nice, but would not be able to achieve the same effect as transmitting this data. Because when you have these dots here, and the lower resolution, the downsampled, is actually a low pass, all green grass, how would you know that there are dots? Not even a human would know. When you have a blurred text that has become unreadable, how would you know what's written if not even a human with the best neural network able to interpret text is able to understand the text? So super resolution and upsampling can do some good things for edges, but they cannot reconstruct information that is information, so true Shannon-like information. So it's important to actually encode this data if we want real fidelity. And this is especially important for these guys, advertisers, because if they pay for content, Nike logo, they want the Nike logo to be represented correctly, not hallucinated by a neural network. So it's quite important to make sure that fidelity is there, and LCEVC allows to kind of send these details in an efficient way. So just to get to some numbers, I imagine there can be some questions, and of course you will be able to ask more later. But I put here like the most frequent ones that we get. So first one is like, cool theory, fantastic, you know, these enhancement data, etc. Does it work? So let's show some numbers. Does it really do what it says? Second element, a lot of people could say, well, could we achieve similar results by just downsampling? So instead of sending a 1080p full HD, can we just lower the resolution and so we achieve low bitrate and most people wouldn't notice the difference? You know, is there really an advantage also in the so-called convex hull? How many people here are familiar with the convex hull methodology introduced by Netflix? Yeah, it essentially says if we chunk a video, it's especially important for VOD more than live, but if you chunk a video in chunks and every chunk you choose the appropriate resolution to optimize the quality rate curve, you know, does LCEVC still bring a benefit? Number three, will it still be useful for future codecs? We talk a lot about AV1, about VVC, about EVC, MPEG-5 Part 1, which is totally different from LCEVC, which is Part 2. Will LCEVC still be useful for those codecs, or it's just AVC and HEVC? What about processing power? So what are the numbers of processing power savings? And most importantly, how can you try it? So let's start with the first one. So cool theory, does it work? At MPEG, there were a lot of tests done on a lot of clips. I imagine that more data will come out soon. But just to give you a sense, the approach was tested on a lot of clips, a lot of type of clips. So, you know, both natural and unnatural. So, you know, also synthetic clips, spanning the whole spectrum of temporal complexity, spatial complexity, simple clips, sports clips, high frequency, high frame rate, low frame rate, etc. Using a lot of methodologies from objective, PSNR, VMAF, SSIM to subjective, MOS, and a lot of methods. So I'll show some numbers, but there is more available, and if you're interested, of course, we can provide some. And for people that are part of MPEG, there are lots of submissions, like hundreds of pages of documents with numbers. So this is an example of LCEVC enhancing an existing codec, so not a theoretical model. In this case, it's actually X264, very slow. So these curves compare X264 very slow, in this case in uncapped CRF mode, versus what happens enhancing X264 very slow with LCEVC. And you see in red, X264 native, and in blue, X264 enhanced by LCEVC. You see PSNR here. This is a case where PSNR shows a BD rate of 43%, so a pretty substantial benefit here. And VMAF, even higher, about the 45%. So in this case, pretty similar number. These numbers are pretty big. When we're talking about CRF, uncapped, X264 very slow, 45% is a lot. And this is another case, food market, a Netflix sequence. Here we start seeing an interesting phenomenon. I will show it later. PSNR has an odd behavior. Sometimes it follows the same pattern as VMAF and subjective MOS. Some other times it crosses over. This is a case where it crosses over. Still significant benefits with this crossover. VMAF about the 36%, so pretty large also in this case. On PSNR, this is a case that shows even more what I was mentioning. This is Basketball Drive, a very famous sequence for people that are familiar, a basketball sequence. Here, PSNR, still decent benefit, at 20% on average, but with a crossover. VMAF doesn't see any crossover and sees benefits up to the highest qualities. And most importantly, MOS, so subjective viewing according to formal subjective tests, sees a 43%, so much higher benefits than the metrics with no crossover. If we go and look at what happens, subjective, of course, is right. And it's very difficult to show it here because the projector is not a particularly good one. So you probably will not be able to see what I wanted to point out. But on the right, it's actually much better, despite 23% less bitrate. But here you would see, probably you can still see it, that there is some evident blocking and bending. So what happens with the native codec is that the image starts collapsing, creating visible quantization noise and blocking noise. While instead with LCEVC, the ability to push more bits per pixel on the base does not make the base collapse, while still keeping some details like the 8 here quite clearly recognizable. So a much better picture, more consistent with the details that matter, despite, in this case, 23% less bitrate. Interesting thing also, when there are details involved, there are more details and more consistency at the same time with LCEVC. Here you can see that in the native, the bars disappear. Sometimes they come and go due to blocking, while instead they are properly reconstructed on LCEVC. The face of this guy, he loses the nose, which is properly reconstructed there, despite, in this case, 36% less bitrate. So pretty consistent picture, consistent with visual quality scores. This is actually funny because it shows why PSNR sometimes is not, for some reasons, not to be trusted. We are still trying to figure out why sometimes it says one thing and sometimes another. But in this case, you see that the scores in PSNR are exactly the same, while from a visual point of view, there are very visible blockings on the left. It's quite impaired, while the right is much more consistent and preferable. So. Yeah. So, the story is, again, consistent also for X265. I will go over it, but it's a very consistent story. I would just like to point out that the distance between the curves is very similar for X265 versus X264. So between AVC and HEVC, the type of benefits seem to be extremely consistent, so they don't get reduced. Also with HEVC, sometimes we get this crossover that is not reflected in VMAF and in subjective scores. And also for HEVC is the same story. So there is, you cannot see it probably here, but there is like more consistency in places where there would be blocking and bending artifacts, and at the same time the sharp details are preserved better. The interesting thing when looking at VMAF, so a more consistent score or subjective, the benefits go for most sequences up to VMAF 100. So they, even for very high qualities, they go all the way up. In terms of convex hull, also in convex hull we see the same benefits. So in convex hull, what happens is that at one point in the ray distortion curve, it's better to switch to a lower resolution, like 720p. And you can see here for X264, the 1080p curve is below for this sequence, which is ducks take off, a pretty complex clip. It's better to encode it at 720p. The scores are higher. Also for LCEVC, there is a convex hull. So you see from a certain point downwards, it's better to use 720p also for LCEVC. But 1080p can be maintained for longer. And in general, the convex hull is higher. Also, quite interestingly, when comparing points at the same VMAF, the possibility to maintain a higher resolution is also reflected by more depth in certain moments, because LCEVC can, in this case, the scores are the same, but the LCEVC encode is sharper. Again, the projector doesn't render justice, but the charts are available. You will be able to see more details in the birds and a sharper water, etc., etc. And again, very similar picture for X264 and X265. This is the same clip of rush hour. This is X264, and this is X265. You see with X265, everything becomes better, but the distance between the two curves is pretty much similar. So the type of benefits are very consistent. What about future codecs? So AVC and HEVC works well. What about VVC, EVC, AV1? Much less data here. There has been a university that started doing some data, but the first results are very promising. Despite no calibration, what we would expect is that with codecs that are much more efficient, the benefit becomes less, of course, but the processing power benefit becomes more. This is what we see with the fact that the first results are extremely promising. So without any calibration and just a first attempt, already on metrics, we are talking about benefits in the range of 15 to 20% for VVC, so over VVC, which is an extremely good codec, with a story that is extremely consistent. So you can see here VVC and EVC, so the two contenders of the MPEG family. And you can see the same story as before. So LCEVC makes, again, it's probably better to watch it when you will have it available, but details are more detailed, and some impairments, like evident blocking impairment here, disappear with LCEVC. So a very consistent story also for the newer codecs. Also very consistent in showing that benefits in subjective are higher than benefits in metrics. This is one of the lucky cases where PSNR doesn't cross over, but you can see about 10% in PSNR and about 20% in VMAF and about 30% in visual, which is quite brutal. Again, it's only, they did it on 2 clips, so it's not a lot, but very promising results. Processing power, that's the easiest to see and easiest to measure because, of course, it doesn't depend much. This is very objectively measurable instantaneously. With X264, very slow, we're talking about 2.4 times faster encodes overall, so it's pretty significant benefits in terms of processing. For medium, we're talking about 1.8 times, so about 2 times. Then, of course, it depends on the server that you use, but these are kind of on I believe they were done on a C5 of AWS, but the numbers are pretty similar with all machines. HEVC, closer to 3x. With VVC, we're talking about 4.7 times for the theoretical model, but we expect that when a product will be available, probably there will be more in the range of 3 times to 4 times. The same is also true for AV1. So pretty significant benefits. If you remember what David Ronca was saying at the beginning, what if we had something that is twice as fast and compresses the same? Actually, LCEVC already does better than that because it's more than twice as fast and it compresses better. So it's pretty nice. So the point is, can you try it? Can you verify these numbers? How can you access them so that you can try it yourself? We are doing our best, all the kind of LCEVC army, let's say, to make it available as quickly as possible. There's already an LCEVC sample player that you can download currently for Android, but also the one that I was using earlier for Windows will be in the Windows Store hopefully today. But if you go to the website lcevc.com, you will see where you can start trying stuff. And immediately, if you go there for Android, you'll be able to download the APK directly from the website, or it should be on the Google Play tomorrow, Google Play Store tomorrow. And then on the Apple Store, it's taking a little bit longer for approvals, but it'll be out soon. In terms of encoding, there are various options that will be made available as quickly as possible. There are libraries for x86 that can be integrated with FFmpeg and used with FFmpeg. There's AWS Cloud Transcoding, mobile ARM encoding. There are also professional solutions being made available by a number of vendors like SimpleStream or Xilinx was actually showing here their Stream Plus solution and also the Alveo solution available in F1 instances of AWS. We also have as Vinoma a test platform, which you can find from the website there. And there are also commercial encoders coming soon from people like AviWest or Telestream, and hopefully more in the near future. As decoder options, currently there are a range of open source decoders available, like the ones that you can find in the sample player, use ISO player, And there are also scripted HTML5 web players that will be made available soon. They are under testing now. And there are also commercial players coming soon. Probably the first ones will come from TheoPlayer and VisualOn. And that's pretty much it. I would cut it here, and then we can get to questions later. You can find these charts on GitHub. There are also the few lines that are necessary to enable FFmpeg to use LCEVC. It's pretty simple. And you will find, as I mentioned, in the LCEVC website, also a link to our test platform, where you can get, if you put the promo code SMW19, you will have 100 hours of free encoding, so you can immediately test drive it and start doing some encodes, which hopefully should be producing exactly the results that I showed, because it's exactly the same version that was used to produce those numbers. With that said, when you try it, of course, remember that it's not flawless, it's not too good to be true. So if you find anything that is a corner case, there are always corner cases in video, but we tested long enough that we are confident that at least 95% of the times it works extremely well. And so, it's not magic, it's just something that works very well in a number of relevant use cases, and we hope that you can find it relevant for you as well. With that said, I will go to the Fireside.
You took 30 minutes. I think you're good at compression. You compressed this from 45 minutes to probably 30 minutes. But I'll go through some of my questions actually for you. I was part of I was talking to you from before the standardization days, and I have the chance to to see this growing a little bit and reaching this point. But I would ask a few technical questions and then move more of a status of this at the moment. The first question I have is something you touched base briefly, decoding speed.
Yep.
So how does the decode, you mentioned the encoder savings about 3 or 4 times compared to current encoders, but what is the decoding solutions available or offering, and how much do you think of complexity this will add to the decoding?
Yeah. The beautiful thing, and it's actually by design, not by luck, is that the codec was designed to be decodable extremely fast, using the pipelines that are already available for graphics. So essentially anything that is able to decode video needs to have scalars, because it needs to rescale to the screen resolution, and it needs to have something for overlays, for subtitles or stuff like that. So essentially the type of instructions and hardware acceleration that LCEVC uses is the same that allows to do scaling and overlaying. So any decoder that is able to display video has those pipelines available. The beautiful thing is that even under HTML5, thanks to WebGL, the graphics pipeline and the GPU are available. So those can make decoding of LCEVC very, very easy. So the fact that decoding can happen with the same or even lower sometimes processing power consumption comes from the fact that the base is decoded at a lower resolution, which offloads resources. And then the scaling and residual adding process is extremely fast and typically uses resources in the SoC or in the processor that would be idle otherwise. So even in a mobile phone, the combination of this ultimately results in either the same battery power consumption or even sometimes magically less, but just as a way of balancing resources, it lowers the voltage overall and consumes less. In terms of available decoding solution, currently the way to decode LCEVC is just simply to enable the media player to know that LCEVC is present. So if it's an open source player like ExoPlayer, it just needs to kind of get the extension of ExoPlayer that gets it. The same for AV Foundations or VLCKit or players like those or FFplay. If it's a web player, the web player just requires an extension in JavaScript with a WebGL extension. So it's as easy as like putting one line of code in the web page. And,
so do you have this decoder implemented today, proof concepted? Do you have them evaluated as well?
Yeah, yes, and the ones that I showed earlier, so the one for Windows is actually an MFT-based decoder. The ExoPlayer is used for Android. We're evaluated quite extensively. The HTML5 one as I was mentioning, is being updated to the LCEVC spec because it's been varied in the past months. So they will all be available pretty soon.
Are these open source available for people to use, or are these under some sort of license?
Currently, they are like produced by Vinova, and we are actually studying how to make them available. So for now, we publish them like this, and we are trying to understand what's the best way to make them available for people to use them.
So probably this will.
It's possible that we will open source part of them. Certainly, there will be some open source and some libraries. We are trying to figure out exactly how to do it.
What I'm interested in, at least I'm sure some people here are interested in as well, kind of understand your position from a company offering a standard versus a company as well offering
exactly.
product. So how can you explain that a little bit more? How can you differentiate whoever approaches you? Are you gonna open source this, but it will be a standard that people go and license, or pay licensing fees for, versus are you also offering a product free of charge or at a fee? Do you have a strategy explanation?
Yeah, I know exactly. Also because it's easy to make the confusion because, of course, as Vinova, we were proponents of LCEVC and we are contributors in terms of the bulk of IP. But LCEVC is an MPEG standard, so it was actually developed with a collaborative work involving tens of companies, and actually thanks to the fantastic leadership of people like Tarek that made it better and better, because over the months, what was proposed became a different beast that is much more powerful. We saw improvements in the range of 15% from the start of the project to today. So Vinova was the initiator, but LCEVC is really an MPEG thing. As Vinova, of course, we have products because we were quick at developing optimized libraries, encoders, decoders, but there will be other companies that I guess and I hope will develop LCEVC-based solutions. So we provide some of those libraries, but others will do the same. So as Vinova, we both provide the software selling it. We are studying how we can make available some of this software also as open source, because as closed source it's already available, and both publicly all through us. But we are studying how we can also provide more open source stuff and trying to find the optimal balance.
Initially, as you explained, this was kind of a company initiative, and you're trying to convince people, look at the gains, come and test it. I'm curious to know what triggered this path into standardization. Specifically, I would like to link that to MPEG is busy working on 2 more codecs, and this is the 3rd one. So first of all, what triggers you going that path? And also, how do you fit within this kind of multi-codec all coming within a year or so together?
Yeah. One reason was really that it was easy to confuse LCEVC, that previously of course the father of LCEVC in terms of the originator of the IP was Perseus, which was in the second rendition essentially what was using the same IP and then morphed into this in part. But it was easy to confuse it with another codec, and so going to MPEG was essential to explain that it wasn't a codec, it was actually something that would help any other codec. And so I think it was a very correct move to position correctly the technology. The other thing is that despite the fact that the predecessor of LCEVC was working, it was difficult to adopt it because as a proprietary technology, something bears more risk, because for a large operator, you never know whether the company is going to stay alive, whether there are submarine patents infringed, and not being a standard, there will be liability risks. So it's much better being a standard. The risk management and the licensing are much clearer, and so it's much easier for a large operator or a small operator to adopt it. So.
And how do you feel MPEG coming with 3 codecs? Do you feel there is a competition there, or more, as you explained, that this is more of a top layer, which is fairly working with any other codec?
Well, actually, what we saw at MPEG, as you well know, is that LCEVC quickly was understood as something that is not really competing, but as I described before, it's a bit of a Switzerland of codecs. So it's neutral, it helps everybody and makes everybody better, can also anticipate the deployment of new codecs, as well as helping other ones. So there is a competition between other codecs. Definitely AV1, VVC, EVC are competing, and may the best one win. But the beautiful thing on our side as LCEVC camp is that we are friends to everybody. And,
yeah, fair enough. I mean, as a layer who doesn't depend too much on what is running underneath, I think. I still would like to ask your view of this journey from being kind of a company codec into a standard where, I mean, it brings lots of belief and credits. How do you feel the feedback of the industry started kind of growing all the way up?
Well, you know, my takeaway is that we should have gone to MPEG earlier because it's been an excellent, you know, first of all, the reaction was extremely professional. Of course, at the beginning, for people that were there, you know, we wanted, you know, some people wanted to burn us at the stake because, you know, there was the assumption that it would be all BS, but I was surprised by how many professional people there were who immediately understood when there was substance that there was substance. And so immediately we went from a situation of heavy skepticism to a situation of strong collaboration to make it happen.
Do you think it's a little bit justified in the sense that initially you couldn't tell what is your secret sauce?
Absolutely.
So that brings some skepticism to the picture, but now it's a standard. People know what's going on. Now they can believe in it more.
And we were using the wrong words because also we realized that we were confusing the heck out of people by not understanding that just the use of some words like scaling was associating immediately the codec to other codecs that were extremely different, like scalable video coding or scalable HEVC. And that confusion, we were helped at MPEG to clarify that we were nothing like that, and that cleared a lot of perplexities that previously were in the air.
I think I will not ask you any more questions. I feel I would allow the audience to ask any questions because we don't have time. So any questions specifically for Guido, not for myself.
Is that working? Or? Check. Any questions?
Yeah, I had a quick question about how this would potentially apply to a completely different type of codec, something like JPEG 2000 or JPEG XS, something that's not cosine based at all, discrete cosine based.
That's a great question, yeah.
Which is also really hard to encode on a CPU.
Yeah. No, it's a great question also because LCEVC derives from a body of IP that is the same body of IP that created also another standard that is not the focus of today, which is SMPTE VC6, which is not in MPEG but in SMPTE, the Society for Motion Picture and Television Engineers, the one of Hollywood, etc., the one doing IMF. And that was focused mostly as a ProRes JPEG 2000 substitute because essentially the same technology allows, you're totally right, to encode much faster and much more efficiently also at the near lossless or contribution qualities that are typically what is the use case for JPEG 2000 or JPEG XS. But also for use cases like JPEG XL, so for websites, for publishing, for pictures on a website, etc. So that is already there and works much better. But you are right that also LCEVC as an enhancement could be used in combination of JPEG 2000. So the fact that VC6 works so well on that use case means that LCEVC should work decently well as well on that use case. We never used it for that just because normally we tend to use VC6 for that use case. But it can certainly be used also for images and intra-only video, yeah.
I came in a few minutes late and I came in on your slide where you showed battery power being reduced. I presume that was for mobile devices. How does that work when it looked like on the developer's slide, those SDKs, I'm assuming that's software-based decoding, so is there hardware acceleration there on the decoder options? Because if it's scripted HTML5, that sounds to me like, at least I'm not arguing that mobile browsers are the best place to play LCEVC, but it sounds like battery power would be reduced in a situation where there's some software level decoding going. Is that accurate, or?
Yeah, it is accurate. Normally, especially for mobile, we recommend to go a little bit lower in the software stack than using WebGL, and that's why, luckily, some mobile manufacturers already took pretty seriously to embed LCEVC already at the operating system level, which should make it possible to really lower battery power consumption, because we still need to measure HTML5. My assumption is that scripted HTML5 will not save battery power consumption. I would be happy if it keeps it the same. While instead already when you go with native code, and especially if you can be native code at OMX level or levels where you're not media codec or similar things, then it starts becoming extremely efficient. So absolutely, the same is true also for browsers. It's true that LCEVC is immediately decodable by any browsers, but what we hope, and we're already discussing with guys like Mozilla or the Chrome guys, if they can just whitelist LCEVC, which hopefully they should, then we can use MFT libraries, we can be native, and it's much better for everybody.
Any other questions?
Also for Tarek.
I have a very simple one, just about naming. What do we look for? Because it's not a codec, it's an enhancement.
Yeah.
So, and it's already 5 letters on top of.
Yeah.
So that's a mouthful. So
Yeah.
And do we start with LCEVC with the codec after that, or do we start with the codec with LCEVC?
So in terms of mentioning it,
yeah,
it's a phenomenal question, because we were talking when we approved the standard for committee draft. I had a very nice discussion with Fraunhofer precisely about that, because LCEVC, HEVC is really a mouthful. So one thing that we were thinking, but we accept any proposal, because the codec itself is LCEVC, but the combination should probably be called maybe LCEVC, LCHEVC, maybe just using the LC, maybe smaller LC before, but we should probably open up in the LCEVC.com website some competition to kind of propose the best way to call the combination, because I completely agree. Every time LCEVC, HEVC, LCEVC, it's very long. Yeah. But so I don't have an answer, but any proposal is welcome. Fraunhofer proposed the L small, C small before, which is not a bad proposal. But.
Any other questions? Oh boy.
So what would be the licensing for this codec?
Yeah, thank you. So in terms of licensing, and I can speak for Vinova, as we know today, the bulk of the IP, for what we know, is owned by Vinova, which is a good thing for the industry, because it means that it will be priced low. And our guideline is, if it's confirmed that it's only us, which we will see very soon, will be to price it at the lowest end of MPEG standards. So if you think about the fact that AVC is considered very low, it will be lower than that, with caps for high volumes. And this is also because, as a strategy, it's really very much an MPEG-5 codec. For people that are familiar with the MPEG-5 family, MPEG-5 was born also with the idea of being very easy to license and very friendly in terms of licensing. So we definitely want to uphold that and make sure that it can be deployed pretty quickly, also because it has the potential of software deployment. In terms of practicality, we will try to publish as quickly as possible, but the guideline I mentioned is pretty self-explicative. So it should be quite a no-brainer for anybody that uses it in terms of licensing costs. So I actually coined with the friends at Alliance for Open Media, it won't be royalty-free, but it will be royalty irrelevant in the sense that in the big scheme of things, it'll be pretty much irrelevant. We are also trying to work on how to make sure that it gets deployed in things like browsers as quickly as possible, because as I said, the beautiful thing that it can be decoded with HTML5 is nice, but of course we would aim at having it inside browsers as quickly as possible, as well as inside mobile devices as quickly as possible, which is helpful for everything.
Okay, we're going to have to close up questions now. Thank you, guys.
Well done.